Assalamualaikum and hi. My name is Ayuni binti Zailan and I will talk about the introduction. The introduction is the behavior of methylene blue in aqueous solution where focusing on its tendency to form aggregates like dimer under specific concentration range. First, background. Earlier studies used the Beer-Lambert equation and extrapolation technique to evaluate molar attenuation coefficient of MB monomer and dimer. The application of study involved improving the spectroscopic and thermodynamic understanding of methylene blue in aqueous solution. The methodology has potential use in various areas like analytical chemistry, environmental monitoring, and industrial application. Next, the principle is the resonant virtual equilibrium hypothesis, which explains temperature-dependent absorption change through shift in the electron change distribution between two virtual resonant forms of methylene blue. The objective is the study aimed to improve parameter accuracy using established equation and explore the temperature-dependent spectroscopic behavior of methylene blue monomer, challenging prior assumption and interpretation.
These are the materials that has been used in the experiment. For chemical or substances, methylene blue and deionized water is used. For equipment, UV-vis spectrometer, quartz cuvette, and thermocirculating bath has been Preparation of sample in the UV-vis analysis consists of 4 steps. The first step, analytical grade methylene blue was used for sample preparation. Methylene blue was prepared in deionized water at a range of concentrations from 1.1 times 10 to the power of negative 6 to 3.4 times 10 to the power of negative 5 mol per liter. Secondly, the solution was prepared and analyzed at different temperature from 9 degrees Celsius to 70 degrees Celsius. The temperature of cell was kept constant using thermocirculating bath. Thirdly, the prepared solution was transferred into a UV quartz cuvette. Lastly, the sample was prepared 3 times for each concentration and temperature condition for more accurate results.
Moving on to the next part, to perform the instrumental measurements, the following setup was employed. First, UV spectrometer configuration. The spectrometer was set to scan wavelengths in the range of 200 until 800 nanometer, covering both the UV and visible regions. For the analysis of methylene blue, a specific wavelength of 665 nanometer was selected, corresponding to its maximum absorbance. Second, cuvette handling. Quartz cuvettes, known for their high transparency in the UV region, were used. The cuvettes were thoroughly cleaned with the ionized water before and after each use to prevent contamination. And third, thermocirculating bath. The temperature of the sample solutions was varied between 9 Celsius and 70 Celsius to study the effect of temperature on the absorbance and concentration measurement of methylene blue. The thermocirculating bath was set to maintain the desired temperature during each measurement, and the exact temperature was recorded for accuracy. To maintain the quantitative data, a calibration curve was constructed by measuring the absorbance of the standard solutions across the defined concentration range. The absorbance values were plotted against the concentrations to generate a linear regression equation A equal mc plus b, where A represents absorbance, m is the slope, b is the y-intercept, and c is the concentration of methylene blue. This calibration curve was then used to determine the concentration of methylene blue in unknown samples by interpolating their absorbance values into the equation. The influence of temperature on the absorbance was also investigated, as temperature variations could potentially alter the dye's absorption characteristics. Absorbance measurements were repeated for each concentration at different temperatures, and the results were analyzed to observe any significant temperature-dependent changes. The concentration of methylene blue in the samples was calculated using the Beer-Lambert law, where the absorbance A is related to the concentration C by the equation A equal to epsilon Cl, with epsilon being the molar extinction coefficient and L is the path length of the cuvette. So the concentration was calculated as C equal to 16.67 mol per liter. This method provides a reliable and reproducible means of quantifying the presence of methylene blue in wastewater, essential for assessing the effectiveness of treatment processes in the textile industry. By analyzing the effect of temperature on absorbance, the study also highlights the importance of temperature control for accurate dye concentration measurements.
Now we are at the result part, and figure 1 shows how a substance observes light at different wavelength. It observes most at 610 nanometer and 664 nanometer. The smaller graph shows the ratio of these peaks decrease as in concentration rises, especially at higher temperature. In figure 2, it demonstrates that molecular binding weakens as temperature increases, with stronger binding at lower temperature. In figure 3, it illustrates that at lower temperature, more molecules stay bound. Higher temperatures lead to fewer bound molecules, indicating weaker interaction. In figure 5, it highlights that as temperature increases, molecular binding weakens, and the structure shifts from dimers to monomer. In figure 5, it shows how temperature reduces light absorption at 660 nanometer but increases another type of absorption, suggesting structural change. In figure 6, it compares two molecular states, showing that one has lower dipole moments while the other one has higher, reflecting a structural and polarity change. Figure 7 explains temperature effects on two states of a substance, showing changes in light absorption around 660 nanometer with experimental data matching theoretical predictions. And in figure 8, it examines how monomers and dimers differ in light absorptions. Dimers observe more at 664 nanometer, while monomers dominate at 610 nanometer, with temperature influencing this balance.
Good day to Mr. Teo. In this data analysis section, we will divide it into three main topics, which is optical and thermodynamic parameters, refuting the invariant monomer assumption, refuting the colorless monomer assumption, and the resonance visual equilibrium hypothesis. I will discuss the refuting the invariant monomer assumption. It is widely used assumption in previous studies of methylene blue that the monomer absorption spectrum is not dependent in temperature. It was later discovered that this assumption is not correct and became the primary source of inaccuracies in previous studies of methylene blue. One of the key findings in the paper that refute the invariant monomer assumption is the temperature dependence of methylene blue. It was found through the experiment that the molar attenuation for the methylene blue monomer at 664 nanometer decreased as temperature increased. It is a reduction from 8 times 10 to the power of 4 liter per mole at 9 degrees Celsius to 7 times 10 to the power of 4 liter per mole at 60 degrees Celsius. In contrast, the molar attenuation of the dimer remained constant regardless of the temperature changes. These findings highlight the importance of revisiting assumptions used in earlier studies of methylene blue. The next key finding is a high accuracy of derived parameters. The error minimization method produced a value of 1.6 times 10 to the power of negative 14. It shows the reliability of the result. However, the molar attenuation of dimer remained constant. The thermodynamic parameters derived from the monomer or dimer equilibrium is as follows. The last key finding that refutes the invariant monomer assumption is monomer and dimer spectra. Monomer fraction increases with temperature and decreases with methylene blue concentration, confirming that the temperature affects equilibrium constant and light absorption properties.
I am going to present the part of refuting the colorless monomer assumption. The colorless monomer assumption, which claimed that the colorless form of methylene blue monomer explained for its temperature-dependent absorption behavior in MB spectra. The experimental data shows that the idea of colorless monomer assumption is invalid and present alternate theories that contradict the assumption. First of all, the experimental data contradict the colorless monomer assumption. In contrast to the assumption, Figure 5b demonstrates that the molar attenuation coefficient at specific wavelength, such as 650 to 690 nanometer, either stay constant or rise with temperature. Secondly, the refusal of other ideas. The possibility of MB monomer absorption on the cuvette walls, which will result in increased absorption at higher temperatures, was disapproved. Thirdly, the support for a single monomer model. Temperature-dependent variation in the dielectric constant of water result in alteration in the electronic charge distribution of the monomer, which alters its absorption spectrum as seen in Figure 4. The theory of resonant virtual equilibrium, which described the monomer as a hybrid of two resonant forms, with their proportion changing with temperature, is consistent with it.
So next, I'm going to talk about the data analysis and discussion of the resonant visual equilibrium hypothesis. The study introduced a hypothesis to explain the temperature-dependent absorption behavior of methylene blue. This hypothesis posits that the observed spectral behavior results from a visual equilibrium between mesomer 1 and mesomer 2, governed by a temperature-sensitive equilibrium constant. The distribution of charge in methylene blue monomer fluctuates based on temperature, moving closer to mesomer 2 structure as the temperature rises and the water polarity will decrease. So first is the dipole moment and charge transfer. Experimental and theoretical dipole moment value for methylene blue grounds excited state suggests a large shift during electron excitation with a charge migration from the sulfur atom to the exocyclic nitrogen. These charge distribution align with theoretical prediction and support the presence of the resonance structure in the molecule electronic state. Second is the solvent and the temperature effect. Methylene blue charge distribution is influenced by solvent polarity, a phenomenon known as a solvatochromism. Methylene blue display a weak solvatochromic response compared to a typical betaine type probe. Yet it still shows a betochromic shift which is the red shift in polar solvent. As temperature increase, a small blue shift in methylene blue absorption maximum occur, associated with a decrease in water dielectron constant. This thermosolvatochromic shift underscore how solvent and temperature module methylene blue absorption properties.
There are a few steps of precautions in the UV-vis spectrometry measurements. The first precaution is controlling the dye concentration. Ensure the dye concentrations are prepared accurately, as deviations can impact results significantly, especially at low concentrations. Second is the temperature control. Use a constant temperature setup for measurements, as variations can alter the spectrum and affect accuracy. It is also recommended to repeat the measurements at least 3 times to increase accuracy and its reliability. The fourth one is minimizing the error. Calibrate the spectrometer before measurements to avoid wavelength shifts, particularly around key absorbance peaks at 610 nanometer and 664 nanometer. Lastly is the spectrometer calibration. For methodologies involving error minimization, use robust computational methods such as solver in Excel to manage deviations in parameters accurately.
So good day everyone. So I'll be talking about the natural dyes, one of the types of dyes used in the textile industry. First, let's define what natural dyes are. These are dyes derived from natural sources like plants, insects, and minerals. They have been used for centuries in traditional dyeing methods. So natural dyes are sourced from plants such as indigo, henna, and turmeric. Next is animals such as like conical insect for red dye and Tyrian purple for sea snails. For minerals like ochre and malachite green from copper. There is advantage of natural dyes include they are biodegradable and eco-friendly, so this making them safe for the environment. Next, they are hypoallergenic, meaning they are gentler and safer for sensitive skin. However, there are some disadvantages. Firstly is natural dyes have limited color range and are often less vibrant. Next, they have lower durability, so that means the color may fade faster. And lastly, producing them consistently in large quantities can be challenging. So in conclusion, natural dyes are sustainable and eco-friendly choice, but they also have some limitation in terms of color and durability. So next, I'll talk about the categories of synthetic dyes, which are widely used in the textile industry due to their versatility and durability. So let's go through each category briefly. First is directly dyes. These dyes are soluble in water and directly applied to fabric. For example is Congo red, which is often used on cotton and other cellulose fiber. Next is reactive dyes. So these dyes form strong covalent bond with fibers and making the color more durable and long-lasting. A common example is Procyon MX dyes, which is frequently used for dyeing cotton. Next is disperse dyes. These are used specifically for synthetic fibers like polyester as they are insoluble in water. For example is disperse blue, which is provide excellent color for synthetic materials. Next is acid dyes. So the acid dyes are used on protein fibers such as wool and silk, and they work well in acidic solution. For example is alizarin yellow, known for its vibrant shades. And lastly is basic dyes. So these are cation dyes used for acrylic fibers and modified nylons. So the common example is methylene blue, which give intense colors. So in summary, each type of synthetic dye has specific application depending on the fiber and the desired properties. Their variety and effectiveness make them an essential part of textile production.
Methylene blue dyes exhibit high affinity for water, high thermal stability, and due to its non-biodegradable properties, so it is very significant to remove it from effluents in wastewater as it can cause adverse effects to human health, which includes anemia, dizziness, headache, fever, nausea, diarrhea, vomiting, skin, mouth, throat, esophagus, and bladder irritation. There are so many methods to remove MB residues. It may be by adsorption, biological treatment, membrane filtration, liquid extraction, advanced oxidation process, and photocatalytic degradation. However, in this case, we are more focusing on photocatalytic degradation as it is the most employed method in industrial application. So this is the mechanisms. It starts first with the electron hole pairs formation. So as we can see, the photocatalyst we use is titanium dioxide. So we can use light sources, for example the sunlight or the UV, where it strikes the titanium dioxide producing electron-hole pairs formation. So the photon energy should be greater or equal to 3.2 eV for this case, and then the oxygen gets reduced by the excited electrons of the conduction bed producing the superoxide anion radical. The water gets oxidized at the holes of the valence band, producing the hydroxyl radical. The superoxide anion radical then gets protonated, producing the hydroperoxyl radical, which tends to combine to produce hydrogen peroxide, and dismutation followed with the dismutation of oxygen. The hydrogen peroxide then gets decomposed, producing another hydroxyl radical. Lastly, the MB residues then gets oxidized by this hydroxyl radical, producing water and degradation products. The MB residues can also get oxidized directly by the holes of the valence band, producing any other degradation products. So we can see that this process is efficient as it is cost effective and use sunlight or UV sources, non-toxic byproducts, which mainly involve water, carbon dioxide, sulfate, and ammonium ions.
The conclusion summarized the study's novel finding on methylene blue self-aggregation in water. A new methodology based on the Beer-Lambert equation accurately determined visible light absorption spectra and thermodynamic parameter for MB monomer and dimer. It identified a thermosolvochromic effect in monomer spectra as a key source of inaccuracy in past research, rejecting prior hypotheses like the colorless monomer theory. The study proposed the resonant virtual equilibrium hypothesis, explaining temperature-dependent spectral change through shift in electron charge driven by water dielectric constant. This approach allows for precise evaluation of virtual equilibrium parameters and molar attenuation coefficient, offering fresh insight into methylene blue spectroscopic behavior and its underlying mechanism.